Okay, I am Dr. Mu'tasim Taha, and I will be talking about how to use the our software db-CICA docking-based comparative intermolecular contacts analysis. This is an example protein with a docked set of ligands inside that protein. As you can see, we have here the docked compounds in the binding pocket. In order to build db-CICA model for those compounds, you need to do the following. First, you should remove, or you should extract the water molecules of the protein structure. First, you can do Control H to see the hierarchy of the protein structure, and also you need to have Control T to see the details, the other details of the protein, including the atoms, amino acids, residues, co-crystallized ligands, and so on. The first step to perform a db-CICA modeling of this target is to extract the water molecules. So you should select them, like in this case here, cut them, and place them in a new page. Here you can see the water molecules of the protein structure. Then you need to go back again to the docked complex of the ligands inside the protein. You need to select the ligands first, all the ligands, the docked ligands, and then invert the selection. In this case here you are actually selecting the protein as well as any cofactors inside that protein. In this particular case you have only the protein structure. Then you need to perform a distance analysis or neighborhood analysis. So you go for intermolecular neighbors. It takes some time to calculate the intermolecular neighbors, as you can see here. Now, in this case, we do have another ligand inside the protein other than those that were docked, so we need to remove this ligand. In fact, it's not related to the docked ligands. So what we'll do, we'll delete the neighborhood again this time. I selected the neighbor monitor and I deleted the neighbor monitor. It's now deleting it. I have to look into the other ligand to see to remove it. As you can see, we have some other ligands here. These are, it seems, they are some ligands related to the crystallization process, and they are not really our co-crystallized ligands, so I'll just delete them. They need to be removed before performing db-CICA analysis. So I deleted them right now. Now we go back again, we select the docked ligands. We invert the selection so that we select the protein itself. Now we perform intermolecular neighbors analysis. Okay. As you can see here, we have neighborhood distances extending from each ligand, each docked ligand with the protein structure. The distances are actually between each ligand and the protein, and not between the different ligands themselves. If you go down here under neighbor, you will find a list of each amino acid, each atom, and the corresponding molecule. Here we actually give the molecules, the docked molecules, names related to their sources. For example, this compound was taken from this journal, Bioorganic Medicinal Chemistry Letters, 2009, from this author. This is the first author, and this is the code of the molecule inside the article. This is our code. This is our serial number. And also we encode the IC50 within the name itself, as you can see. Anyway, here you find the each amino acid with the atom and the corresponding ligand that is close to that amino acid. And if you go down here, you will find the distance between those two. So, for example, if you select this one here, well, sorry, back again. If you select this one, which is this distance 57, 28, let's go for 57, 28 here, 57, yeah, and as you can see, this is the distance I'm talking about. Let's show by radius here to restrict the number of atoms to see things clearer. Yeah. For example, this is the distance here between this atom of this molecule, 5728 Sato, and the near one of the atoms inside the binding pocket. And the distance here is measured to be 4.67 angstroms. So if you select this distance here, right hand click, you will find it to be 4.67 angstroms. So at the end of this analysis, really, you should have a list of all ligands here and their distances from all atoms inside the binding pocket, as you can see here. So now we have selected the atoms, the ligands, and their corresponding binding site atoms and their distances. We will copy this now and paste that in a text document. It will take some time during the copy because we have lots of lines here. Okay, it's now finished copying. We'll paste that in a text document. Preferably a document opened using Notepad++. So now we will paste that. As you can see here, the atoms from the binding site, aspartic 194, and the corresponding ligands, together with their atoms, in fact, atomic ligands, are shown here with their distances. The distance threshold that I allow in the neighborhood analysis is 5 angstroms. I think this is enough. As you can see here, it's the distance attribute is 5 angstroms. Okay. So we have now, as you can see, around 100,000 lines corresponding to the different neighborhoods. Now, we need to carry the same analysis now for the ligands inside the water molecules of the protein. Here I will enter that to start with a new line. Okay, so we go back here. We delete this neighborhood to release some RAM for the machine. So go here and delete. Okay. These are the ligands. Now, we will copy the ligands, same ligands in their same positions. Copy and paste them within the water molecules of the protein, because we need also to analyze the contacts of the ligands with the protein water molecules as well. So this is how they look here. Sorry, this is RAM issues. It's okay. This is how the protein now, or how the ligands now are placed within the water molecules of the protein, which we removed as the first step during the analysis. Now the next stage is to invert the selection, as we did before. Now the water molecules are selected, not the ligands, and to perform the same neighborhood analysis. Here we have distances between different ligands and different water molecules within 5 angstroms. You go back to the neighborhood monitor here, and you will find each ligand. This is the name of the ligand, and this is the water molecule, and here you find the distance, of course, up to 5 angstroms. We will do the same. We will just copy that. You can multiple select using Control and copy that. And then paste it again into the same text file. Yeah. So now the text file is ready for conversion into binary matrix, binary contacts matrix. We will save that as test. Save. Now we don't need to see the Discovery Studio anymore, so we'll close it. Now we have the text document ready for the next step. The next step has to be done using MATLAB. Okay. In MATLAB, you run the AA tool or the db-CICA tool. The first thing you need to do is to convert your text file into binary matrix file. Text file, original file, into binary matrix file. Browse it. This is the test here. In fact, you can actually upload several files together, and it can convert them one by one automatically. Here the binary file. Here where you want to put the binary file, we will put it at the desktop. And here we can press convert. In this case here, we actually have an option of extracting the activity data directly from the names. Because we write our names of the molecules in a specific way, we can use this function to extract activity from the name. I don't recommend that you use that. You can add your activities later manually. We will show you how. Here the distance threshold. In our original article, we decided that the threshold for contact is 2.5 angstroms, such that if the distance is more than that, the binary matrix will be 0. If the distance is less than that, the binary code will be 1. So we will stick to 2.5 angstroms. Now it's converting. You can check if it's converting or not by minimizing the structure. You will find that the MATLAB interface will look a little bit strange, which means that it's actually running right now. Okay, it finished generating the binary matrix. Let's see how it looks. This is the output binary matrix. Please remember that our package is only compatible with Excel 2003. It's not compatible with newer versions of Excel. Okay, we will open it. Sorry, it is in the directions are okay. This is how the binary matrix now looks. Okay, so now you can see the molecules here. These are the ligand molecules, and these are the amino acids. Each column corresponds to certain amino acid atom inside the within 5 angstroms within around the ligands, and each one of those points indicates whether this ligand is actually within 2 angstroms, 2.5 angstroms, or not from this binding atom here. For example, this compound here is within 2.5 angstroms from this amino acid atom. The atoms are coded as in DiscoveryStudio, HB2, C, CB. These are codes given to amino acid atoms. Usually they are the codes provided by the PDB within the protein data bank. Unless they are hydrogens, hydrogens are given code by the DiscoveryStudio software. So now you have the binary matrix ready. Everything is okay now. You need to add the bioactivity for each compound at this level. This can be done once, really, because the compounds are ranked, aligned according to their names. So you need only to add the activities only once. You need to add the activities as negative logarithm activities. So you have to add here minus log activity. You need to add this number here, this column here, and you need to convert the IC15s into minus log activities. I will add the numbers here. In fact, I have done that before. I do have the binary matrix ready. I'll take the numbers from here. Sorry. Okay. Seems that I don't have the numbers on me right now. Anyway, we can add we can add random numbers just for the sake of the study. You need to remember that db-CICA is a supervised modeling method. You need to have the activity of the compounds ready so that you find the contacts that correlate with the activity. Those contacts in the binding pocket that explain bioactivity variation. So it is actually a supervised modeling approach. So you need to have bioactivity data. Unfortunately, I don't have them right now. Okay, here we go. So this is the binary matrix. Now, once you have the binary matrix ready, this is the text file. We extracted the binary matrix from the text file. We added the biological activity in the logarithmic format for each ligand. Now, we can run the second step, which is to convert binary file into best combination file. Here, best combination file is the actually db-CICA model that is. So we need to load the binary file from the desktop. Okay, so the binary file now. This is the binary file. It's the test text binary file. Then we go for best combination file. We will ask the software to put that in the desktop. Now we go for convert. Here, select this selection here, positive then negative. What we mean by positive then negative is to first look for, first you need to, what the software does is to identify directly correlating columns or summation of columns, and directly correlating columns and negatively correlating columns. Those contacts that are directly correlating and those contacts that are negatively correlating. The negative correlating columns are taken out temporarily, and the positive correlating columns are used to sum, to build sums using genetic algorithm for column selection. So genetic algorithm is used to select combination of positive columns and sum them up. Now, the number of columns that we would like to evaluate as positive columns is in this line here. So we will use genetic algorithm. I usually order the system to screen from 4 to 10 combinations. That is, look for column sums, contact sums that include 4 columns up to 10 columns of directly correlating contacts. So you might have 4 column summation or 5 column summation or 6 column summation up to 10 column summation. The selection process is done by genetic algorithm. Here the negative columns can be placed in this position here. We usually go for maybe either 5 negative columns or 10 negative columns. I will try here 10 negative columns. So what I'm doing here, I'm asking the software to attempt finding the best 4 columns, 5 columns, 6 columns, 7 columns, contact columns, which I mean contact columns are those, in fact, if you go to the binary matrix here, for example, 4 columns, it may be this one, this one, this one, or this one. If you sum them up, you check the summation, is it collinear with the activity? Does it correlate with activity or not? If it does, then put this solution as a potential solution and look for some other possible solutions. If it doesn't, throw it away. And once you have a set of good solutions, allow them to mate with each other. Allow them to match, to mix and match with each other in a genetic Darwinian way. You carry out that for 4 columns, 4 membered columns or chromosomes, 5 membered chromosomes, up to 10 membered chromosomes. This is what I mean by columns here. While negative features are taken out after being inverted and attempted to look for the best negative columns that, upon summation with the positive columns, can yield good correlation with biological activity. You can read actually the article in details, our initial article in details, to understand what I'm saying about. Now, here you determine the cross-validation method. We normally go for k-fold, which means that you have to divide the data into 5 groups, random groups, and then build models from 4 observations and use the 5th for testing. Repeat that 5 times for each solution that you select here. This is the success criteria that we used. The fitness function that we look at is usually R-square. So a good solution has got high R-square, high k-fold R-square. Here you save the best 10 solutions, as you'll see now. Regarding the parameters, these are genetic algorithm parameters. Here the population size that we start with is 100. Usually we go for 100 chromosomes, and we carry out the calculations over 1,000 generations. So the number of iterations are usually 1,000. The starting number of random chromosomes is 100. I usually go for one elite count of 1. You can refer to the article to understand those points in more details. We don't stop at fixed length because we are looking for variable lengths starting from 4 features up to 10. So we'll keep that without checking. Now, here what we mean by feature weights: allow a single feature to emerge up to 3 times. That means a feature can have a weight of 1 or 2 or 3. Here we go for each number independently. What we mean by that is to carry out the analysis for 4 features independent of 5 features or 6. I mean, here you look for the best model out of 4 featured models, and you look for the best model out of 5 featured models, and you look for the best model out of 6 featured models. Don't look for the best feature out of all of them. For example, you might have certain, maybe the best model from 4 to 10, from models of 4 to 10 chromosomes might be an 8 model with a very high R-square. If you don't press that, it will only show you the best model, which is number 8, the one that have 8 chromosomes. If you press that, then it will show you the best out of the 4 models. You might have thousands of 4 featured models. You will have the best one of them. You will have the best one out of 5 featured models. You might have thousands. So it will actually give you the best models for each number of features. Pressing this. I recommend pressing this actually. So now we will start running. Okay, we have an error here. The error probably because we have an empty cell here. We have to fill it. And we need to close, save the file in old format, in Excel 97 2003 format. Save. We call that binary. Okay, save. And then close it. Close the Excel. Okay. So here, where is the binary? This is the one that we are going to work with. Once again, run a tool, convert binary file to best combination, load the binary file. put the output here. Okay, we go for positive then negative. Use genetic algorithm from 4 features. Here 10 to 10 or maybe 5 to 5 to make calculations quicker. Use k-fold, use feature weights. Here the parameters, you can go for population size of 20 up to 100 generations just to make things quicker. And let's run it. Okay, done. Let's see the output. It's given the name binary out. We start with binary and we end up with binary out. Once again, it has to be in Excel 97 to 2003 format. We will open that. As you can see here, look, this is how it looks, the output. Sorry for the direction of the Excel. It's in Arabic, that's why the direction is opposite to English. So this is the first sheet in the output file, binary out. Here in this sheet, you can actually identify the contact atoms that were positively correlating with activity. These atoms, for example, lysine 82, He2, which is one of the lysine atoms, correlated activity. This water molecule is also correlated with activity positively. Their summation. The summation of those together correlated with activity. Those with not here means they are negatively correlating. They are bad contacts. They correlate negatively with activity. And here the numbers here are the statistics. This is the R square of the k-fold. This is the leave one out R square. And this is R square, simple R square or resubstitution R square. The next sheet here, sorry for the direction once again. This sheet shows the number of contacts for each molecule in the training list. If you in the list of compounds, if you go back to the binary matrix here, you will find that. Sorry, let's go for the binary matrix that we gave to the software. This one. Here, for example, this compound made 5 contacts with the rest of the binding site atoms. Okay, so this compound made 5 contacts, not with the rest, in fact, with the with those significant contacts. So the summation of contacts done by this compound is 5 with those particular amino acids, positive amino acids and inverted negative amino acids. So the first one made 5 contacts, the second made 4 contacts, and so on. For example, this one made 11 contacts with those particular positive and negative, with positive directly positive and inversely with negative contacts, and so on. You see, this is the third sheet. Once again, the third sheet is the model that is based on 5 contacts. The first one was based on 4 contacts. If you calculate them, you have this one as 1 contact. It's the same amino acid. Water 112 is another contact, second amino acid. Water 180 is the third contact. It appeared only once here. And water 56 is a fourth contact. It appeared twice. So we have 4 contacts here. 4 contacts. 1, 2, 3 alone, 180 alone, and 5 is 56. The nuts, the bad contacts, are in fact, as I said, 5 only. 1, 2, 3, 4, 5, and we do not allow weights for negative contacts. So each one of them appeared only once. The third sheet here shows the model of 5 features. 5 features. So we have now, this is 1 with the weight of 3, alanine 80, HB3. This is 2 with a weight of 2, cysteine 133, O. This is 3 with a weight of 3, water molecule 112. And this is 4, appeared only once. And this is 5th, appeared 3 times. So we have 5 contacts here in sheet number 3. As I said, this one, in sheet number 1, resembles the best product of 4-featured model. And the one in sheet number 3 resembles the best product in 5-featured models. The sheet number 5, the best product in 6-featured model. And so on. Okay, and if you go back to sheet number 3, the next page here shows the summation of contacts